Hi, everyone. This is a talk about the current state of nested virtualization. We're going to look into basically what's been going on and recent changes, things that work, things that don't work. We are not going to dig deeper into the technical details of why something is not working, but we're just going to do a broad overview. And a few things before we start. So we're trying to cover both AMD and Intel, although the fact is that most of the presentation is actually about Intel. Primarily, I'm sorry?
Because AMD only works for 5 years.
Right, yes. Primarily because there hasn't been many recent changes, and that means that the code is stable. Of course, I'd like to introduce myself. My name is Bandan Das. I'm a software engineer at Red Hat. I'm here with Kiszska from Siemens. And Yang Zhang from Intel has inputs to the presentation, but he unfortunately could not make it to the forum. So let's start. So this is the outline. We have our obligatory introduction for people who are new to it, and then we're going to look into what's going on AMD, what's going on Intel, and do some quick evaluation of what kind of hypervisors work in the nested environment, and some evaluation as well. Jan is going to cover issues over migration support, and also some of the recent work on nested IOMMU. And then we're going to wrap up with questions. Okay, so what is nested virtualization? So it's pretty simple. It's running if you look at the image to the right, it's just running a hypervisor on top of a hypervisor, as you can see here. KVM is the hypervisor that's running on top of hardware, and then you decide to run Xen on top of it, and Xen is a hypervisor too, and Xen would like to run its own guests. So what nested virtualization gives us is that now Linux is actually nothing is being emulated. I mean, of course, not exactly true, but Linux is running on top of the hardware CPUs in guest mode, which is a good thing for performance. And usually if you have been to any previous nested virtualization talks, you would have seen it's mostly associated with turtles, an image of a turtle, and we decided to have something else because we are covering both Intel and AMD, and Jan came up with this idea. So I think it pretty much shows the hypervisor inside hypervisor inside hypervisor examples to the Russian dolls. So this is in no way an exhaustive or well thought of use cases. I know that this is what people are talking about all the time. One of them is in the cloud. A cloud provider could give you functionality where you could run your own hypervisors for certain use cases. And but the most, I think, most common use case these days is testing. I know OpenStack folks have been trying to use it for testing. And also, I think a good use case is debugging or researching hypervisor exploits. The attack vector, I cannot guarantee that it's going to be 0, but at least it would be reduced if you're running in a nested environment. So this is the terminology is very specific to VMX, but if you look at it from a broader perspective, I think it could apply to both the architectures. So VMCS is the VM control structure, which is the data structure that the software creates for the VMX architecture or the SVM architecture. It's called VMCB for AMD, I guess. And then that's being used by KVM, which is L0 here, level 0, to create a guest, which is Zen in this case, which is level 1. Now, Zen is a hypervisor too, so it tries to launch its own guest. So it creates a VM data structure, VMCS 1.2, in its own private address space. And the way nested virtualization works is that operation gets trapped by L0, and L0 creates its own copy from the information that's in VMCS 1.2 to directly launch the Linux guest on top on behalf of L1. And then one of the things that frequently happens is when L2 is running, which is the topmost guest, there's a trap or there's an external interrupt, and then what happens is the CPU is going to exit back to L0, and L0 is going to decide whether it needs to run L1 to take care of some bookkeeping, or it can continue running L2 again. And so this back and forth between L2 and L1 keeps on going, and then that's how both the guests make progress moving forward. So I entirely skipped a page for recent changes on AMD because, as he said, there's no changes. I mean, there are. I recall there was a small fix to run, but that was actually to run KVM on top of ESX. So it's not strictly our use case, but still it's nested virtualization. So I think the fact that nested is enabled by default on AMD, that's a pretty good sign that the code is stable. Jan mentioned AVIC, which I didn't know about, but I now know that it's the equivalent of Intel APIC V. And I was told that this was announced a while back, but there's no hardware yet. But it looks like this is a potential case where some work needs to be done if the hardware is out. And then, of course, testing is like a forever thing. Hypervisors change. There are new ones. There are old ones that change. So I would say that's a to-do item that you cannot get rid of. And a good thing probably, I don't know how much work has been done on that, but a good thing probably would be to check for compliance with the specification. Some of this work has been done, we have been doing on Intel, so maybe this is something we could look into if it's required on AMD as well, if we are doing the right thing. We had some discussions yesterday about, I think, doing the same for instructions. So this is more kind of spec compliance with the architecture requirements in the architecture specification. So on Intel, though, we have been seeing changes. The code is not very, it works, but I would say it's not stable yet. As I said before, we have some specification compliance work. For example, what kind of checks we need to do when we VM enter or VM clear, and the addresses has to be aligned, and simple things like those examples. And we added corresponding tests to KVM unit tests so that we could see that we don't break them in the future. Support for MPX was added, which is memory protection extensions, which is kind of a hardware and software assisted checking on bounce checking. So the VMCS fields has fields which control how the guest can use MPX, and now these fields L0 can decide as to what values these fields can have, so that when L1 is running, it has the right values, and when L2 is running, it has the values that L2 needs. We also had tracing improvements. One of the things I remember is now there is a way to trace if we are exiting from L2 to L0, or we are exiting from L2 to L0 to L1. Could help in debugging. We added support for interrupt acknowledgement emulation, which is not very complicated, but it's required by certain hypervisors like Zen and I think also ESX. So the usual path for interrupt, the interrupt path that usually is taken is when the VM exit happens because of an external event, then the hypervisor is going to enable interrupts, and that's when the interrupt gets delivered. With acknowledgement, what happens is when the VM exit happens, the VMX architecture guarantees that the vector information is written to the VMCS. So to emulate it, it's simple. We just write that information to the VMCS for that the level 1 guest has for level 2, and then run L1 so that it knows that the interrupt vector is there. Interrupt injection rework, which is basically when an interrupt comes in, to decide whether that interrupt needs to be injected to L1 or L2. This was inspired by some bugs that were found out when running Jailhouse, hypervisor that Kiszska works on. Incidentally, some of the bugs related to interrupt injection also helped with speeding up Windows execution. So that's about it for this. So this is what we need to do now. Those were the recent changes. That was in no way exhaustive, a very complete list. We have time constraints, so I just picked a few ones that I thought were interesting. So we need to make it more stable. I think, and that would be when we reach a point when we can also enable nested by default for VMX as well. But of course, and this applies to both Intel and AMD, but the test matrix, so many hypervisors running so many guests, which is what makes the testing more complicated, and fixing bugs and finding out bugs and implementing missing features is always a challenge. We still have to look into the specification compliance thing. We have been doing some work, and probably more work will be done in this area in the future. We don't have nested VPID. VPID is basically a tag given to an address space or a translation, so that you don't have to do a TLB flush. So right now, what happens is you just share the VPID that L0 uses for L1 is actually again used for L2, and switching between L1 and L2, we do a TLB flush. A more spec compliant solution probably would be to advertise VPID to the L1 hypervisor as well, so that it can create its own tags, and then we can create a mapping in level 0 hypervisor, that actually tags the real address space. MSR load store, which is a mandatory, according to the specification, is basically a bitmap of MSRs that you need to save or load during a VM exit or a VM enter, and we don't have that for VMX yet. And the reason we can get around it is because I think KVM probably does not rely on this, but it's mandatory, so there's a good chance that a lot of other hypervisors do, which will be probably a little bit more clear when we look into the test matrix that we have. And I was told that Intel is also working on implementing nested APIC-V. So APIC-V is basically a way to reduce VM exits when a peak access occurs by the guest. Exposing this virtual page to level 2 will further reduce VM exits. And I think for IO workloads, this would be a performance gain. So now we come to some of the tests we did. They were not rocket science. It's just basically trying out a few hypervisors, running a few benchmarks. Easy to find, that is. Easy to find benchmarks. So that was my host, which is, as you can see, not very high end. And we tried running these 4 on AMD. We have a much bigger matrix on Intel, but I can assure you that's more embarrassing as well. So Linux works, Zen works, Jailhouse works, which is the hypervisor that I just spoke to you about. ESX, I'm not sure if it's a setup issue, but I could not make it work, especially when launching a guest. That didn't work. And for the test, we did spec JBB. We just ran the backend in the guest. The transaction injectors and the controller was actually running on a different host on the same LAN, of course. And then, tried various SMP options and compared L1 and L2 performance numbers. For the kernel compile, it's the same thing, but we just use time command to measure the time. So this is the kernel compilation, and it looks not bad. The L2 figures are the one in red, and it's all in minutes. It's kind of not the exact time, but just a whole number. You can see that the difference is not that much. And that's the number of vCPUs for 1, 2, 4, and 8. That's the farthest I could go. So it looks like something that just is taking a lot of CPU time, just like Make would do, has good results when running in the nested setup. A lot of I/O-related work, as you'd expect, won't fare that good because you could have a nested file system, and just having the nested architecture, just exposing the CPUs in the nested fashion isn't enough to run a lot of benchmarks. But then we come to spec JBB, and you could see that the performance has been a little bit bad than the last time. So I just removed the scores. Level 1 is I kept it as max, and then this is just a percentage of the score that level 1 has. And you could see that it's a little bit bad than what we saw for the kernel compile. At first, I thought that maybe this is related to I/O, but I found out that spec JBB does not include a lot of disk I/O and network I/O, and that does not contribute to the score that you get. So I'm not sure where the overhead is here. It could not be any emulated instructions, because that would be true for both L1 and L2. It could be no. Okay, but isn't it going to affect both? Yeah. Okay. So there you go. That's one thing that could be a problem.
And you also get pretty big penalties if you allocate memory on the fly, because you have those two level. So we basically have this combined level 2 page table between the nested page table of the second guest and the first nested page table.
Yeah.
So if you depopulate your first level memory, you also get big speed.
So we just spoke about that. On Intel, that's the example hardware that we chose. And we tried a variety of hypervisors as L1, and that's the matrix. So nothing works. It's not that bad. So basically you can see KVM is green, so that's good. And I don't know how VMware Player is green as well. But, you know, I think there's a lot of things that's missing. I mean, now at the moment, the nested word work on VMX at least is so much focused on just getting KVM to work. So I'm pretty sure, you know, a lot of things that are mandatory according to the spec, and we still don't care about these things just because we don't need them in KVM. But of course, that doesn't mean that we don't need to do that. We have to. But this just shows that this is the current status, and we have a lot of work to do, and how complicated it is to make sure that you know, everything works with this. And the same test, kernel compilation, also the same as what we had before. But with spec JBB, we had a really different outcome. And that is this. So I wanted to keep this as a mystery because it would not have been that much fun, but so this is the system that was used to carry out the spec JBB runs, but the kernel compile was carried out using just a standard Haswell desktop processor. The lesson that I get from this is, you know, as long as you can find the right setup to run with nested word, it will work for you. But since Ivy Town EP has a lot more newer features that were introduced, like APIC-V and posted interrupts, I think that is somehow not a good thing. I mean, you can run nested virtualization as long as you find the right setup that works for you. But we need to do a lot of work to make sure that that is not always the case. We have to make sure that it works on every system. So this is a mystery, and we still haven't figured out why this is this bad. It doesn't look like it has to be this bad.
It's not something that you can really compare because the cloud times change and the architecture change. But the architecture that we expose in the VMX is roughly Western. Roughly. As far as the VMX features go. So it's really interesting to see what the comparison between the Western and the IOMMU on non-nested virtualization, and see whether something got sped up by
trying it out with
hardware guys.
So one of the things about spec JBB is it does a stupid number of hit time VAs. So if you're getting this kind of catastrophic performance, I bet you it's hitting a timer that's being emulated. It's really, really slow. So like we're not probably doing nested TV clock for the equipment.
Yeah.
That's most likely there. But spec JBB does nothing other than get time of day, and that's all it does.
So next time, we're not going to try to spec JBB at all. Okay, so we just covered that. So this is Jan's part.
Okay, so I'm online? Okay. So let's look at some other aspects. So let's assume all the rest that we heard before is now solved and everything is fine. We have decent performance and no stability issues. There are still some things to be done. And one aspect is, of course, you may wonder, what about migration? So can I migrate a virtual machine that runs a hypervisor with guests inside today? And the answer is that it's simple, it doesn't work. It's not supported. What do we need for this? Yeah, it's not that trivial actually, because what we are currently lacking simply is to expose in some way or the other the additional state that we get when we run in virtualization mode in the level 1 guest. There is, well, register state, there might be some other hidden states that you don't see through the exposed interfaces of the virtual CPUs right now. So if we just migrate today, we lose the state and we will crash on the target machine, of course. So the question is, well, what to do with it, how to address this? Well, there basically, one option is, or what was discussed, I think back in the time when AMD was at this point, what to do with it. One way would basically to force, if the level 2 guest is running right at the point we want to migrate, to force the level 2 guest to leave and to fall back to level 1. And basically pick up the state from there. That's one way. It's still open to me if this is possible in all our scenarios, specifically if it doesn't violate any kind of specification of the hardware virtualization. I wouldn't be that sure about it. And yeah, well, but it would probably simplify a lot of the things because we don't have to care about the state that we have when we are running a guest in the guest. The other direction is, well, yeah, basically look in details on these additional state and simply extend our current interfaces so that we can pick up the state from user space and as part of the CPU migration, also migrate that part. But still, some work is to be done here. And, well, so far no one really looked into this topic, simply because we were still having other problems. Another aspect, so if we have all the CPU nesting solved, then there's still something else, what you usually have these days on virtual machines. It's the IOMMU. So what are the use cases to have an IOMMU in the nested scenario? Well, first of all, again, testing was what currently also my interest is. Our interest is to have a virtual IOMMU to test our hypervisor in this environment instead of real hardware. But another scenario might be interesting for certain applications is basically passing through a physical device directly from the host towards the level 2 guest. And for this, you also need to expose some kind of IOMMU, of course, to the level 1 hypervisor. There's some history behind it on the QEMU side, so there was some attempt to implement the AMD IOMMU. I think it was 2011 this way around. Problem back then was that QEMU at least wasn't prepared for this very well. So the patches that emulated the IOMMU also had to change a lot in the device models all over the place. So it was not really well accepted from this point of view. Also on QEMU side, there are already IOMMU models existing for other architectures. So Spark is doing this for quite a while with its own IOMMU layer. So this was basically the history. Right now, things look a bit better there. So we have now for quite a while, since the memory layer was introduced in QEMU, also some abstraction for IOMMUs. It's being used already on Power, on Alpha, and since I think early September, we now also have it used for Intel. So we have, as mentioned before in the talk, we have a VTD emulation today in QEMU mainline. It was a Summer of Code project by Li Tan performed this year. It's quite nice work. It was originally based on Knut's work, the baseline basically he picked up. We have DMA remapping emulation available now. So basically all PCI devices we have in a virtual model are now basically being able to export it, pass through from level 1 to level 2. Also the model is addressing error reporting with respect to DMAR, and it even has a cache emulation. Doesn't improve any kind of performance, but it improves that the correctness or the behavior of this model is more accurate with respect to real hardware. What's missing right now in the upstream version is interrupt remapping. Well, I have a working prototype for this. It lacks a lot of features and a lot of tweaks in order to make it usable. but at least it works for the current scenarios. I also think that Knut, you worked on this as well, and you got some things running, SRIOV things, I guess. So there is a baseline available, but we still need to do something about it. So what are the open topics in this area? Well, first of all, what's lacking right now is support to real-world scenario passing physical devices through. So we can only pass through right now emulated devices. So what to do with it? Well, there are basically two directions. One way is basically to not use a user space model for it, but a kernel space model. This is what Will Deacon did in a model for the ARM SMMUs. So he has some existing code power tree out there, and he will also discuss this topic on Plumber's session on Friday morning. That's one way. Well, the other way is reuse the existing user space model and extend it to use VFIO. So the question is basically what is most efficient and what is also with respect to the model we push then in the kernel again. So what we discussed yesterday, how big is our attack surface in the kernel and how big becomes our device model in the kernel. So we have to weigh these pros and cons. Alex.
So Alexei was referring to a lot of these issues yesterday in his power talk.
Okay,
We have exactly those issues. We basically have to emulate an IOMMU to the gas inside the gas, just to be able to access devices at all, because there is no linear mapping by default.
Okay, yeah.
So we have those issues, and they need to get solved very soon to be able to do any device assignment at all.
Yeah, good. Well, good and bad, but we need to work on this, definitely. With respect to interrupt remapping, there's one issue with the current approach we have, at least on x86, that it doesn't work with in-kernel IRQ chip. The reason is quite simple. If you do interrupt remapping on x86, you also remap the IO epic interrupts, but currently there's no interface available with existing KVM in-kernel IRQ chip model to basically intercept the interrupt delivery from the IO epic model to the APIC model. So they just go directly, and you can't do anything about it if you have interrupt remapping model and user space enabled, so we need to extend something there. I haven't made my mind up on how the interface could look like, but something has to be done in this way, unless we pull out the IO epic again and move it in user space. And then, of course, the question is, what about AMD IOMMU? Well, there is a working model, at least from the past, but it would have to be reported on the new infrastructure we have in QEMU. So maybe someone would like to step up, or maybe another Google Summer of Code project. We'll see. Okay, so to wrap up, as we saw, AMD nested virtualization support is in quite good shape. Although we found a little bit bugs in the corner cases when running jailhouse on it, in general, for the most hypervisors, it's perfectly fine. And even those bugs were fixed now. But still, lessons learned from this, and I would say that probably that AMD path is even less tested today than the Intel path, although it's more major, simply because of the exposure to existing use cases. So we really need testing, regular testing. The question here is also to the audience, what about the auto tests? So we have some unit tests on the low-level part, on the micro-level part, but I guess we also should include some higher-level tests, at least some kind of boot-up test. Does Windows run on whatever in a nested environment, or does the other thing run? Just to avoid that we get regressions. On the Intel side as well, same scenario. Probably one of the few issues we saw earlier in the slides are related to recent regression, not only to pre-existing problems. It's hard to test, of course, because of the larger test metrics we have there, but at least some basic things should be done in a regular fashion. That would help. We already have some integration tests by Intel done once in a while. So some things came up from this and were reported, but of course it also have to be addressed. Yeah, and once we have a stable environment, then we need to think about the migration thing. So this was basically mostly postponed to the reason that we weren't sure about which state we really have to export to user space to do migration, up to the point where we really have a complete emulation available. But once this is, well, I think it's pretty close now, and we should really start to think about this. And IOMMU emulation, as talked about, we are approaching to this. We have the basic infrastructure. for this available now, and we should work on this and continue. And then, of course, the question is, beyond this, what about non-x86 architectures? Alex, of course, an answer to this.
Of course, thanks to Heritage, all of this works on Power.
Well, okay, Power solved, fine. What about ARM? I heard this several times that ARM is a problem in nested virtualization. I'm not really sure. I personally didn't understand yet if it's really an architectural impossibility or if it's just hard to emulate in the first step and probably inefficient, but well.
Because you have a special height mode, which you don't have an equivalent in kernel mode for. So you can't just easily try and emulate that in all cases. But it's definitely possible if you just put a small instruction emulator into the kernel, which we usually have around anyways, and just emulate all hypo instructions and then swap it on demand. It's just hard to do.
Alex, Power, does it work always, or does it work only if you have the virtualization?
So on Power it works. So we have two different flavors of KVM on Power. There's the HD accelerated and the non-HD accelerated.
You have three kinds, virtual PR and non-virtual PR.
They're the same. They're basically all USB sector interfaces. They just have slightly. They either use an external page table or internal one, but the rest is the same.
No, but non-virtual PR cannot do the hypercode because it will go straight to zero.
We fixed that up in IOMMU 2.0 also. So we have a hack now in the firmware that replaces the hyper construction with the privilege instruction. In case you're running this stupid, messy code. But it works. So all that works. You just have to run ERKV on top of HTTP. And then it's fast and works better.
So it works also if you get that support. Also if you get it not virtualized.
Okay. So first of all, thank you all. Further questions or need for discussion, so further ideas, how we should progress, where we should progress. Yeah.
Bandan,
Yeah.
shared performance measurements regarding nested and virtualization. How far the software emulations give performance measurement? Did you try?
Software only, emulated? No, but I don't think. Oh, okay. Are you talking about the Intel? Oh, okay. That's a good. Yeah. We haven't thought about. We didn't even expect that that's the result that we are going to get, honestly. But that would be a good thing to see. I mean, how good the software emulation fares in that case. I do think that this is. I mean, it could be just a setup issue. You know, the test setup. It just looks too bad to be true. So yeah. So we didn't try out the emulation only thing.
I think that's too low for our data. We have lots of data. I think they still
This was
It was really
barely visible.
yeah.
This was a setup, right?
Yeah, this was actually done by Yang, and this was his setup.
It's the whole thing. It's about the out-of-the-box experience. So I think there are probably other issues in non-nested scenarios as well, where you just pick the wrong combination and the wrong version of something, and then you end up with something that's totally unacceptable. And this was, of course, an extreme case as well.
I think Fedora 20,
316, I thought.
316.
I think it was a RHEL.
Oh, it was RHEL 6.5, right?
Yeah.
RHEL 6, if you're using a block, one to be so it was the aspiration.
Well, the thing is that we have to get back to this and make sure that what we are seeing is actually right.
So comment regarding S3
some prototype running that the student did as a master's thesis, but you're far, far away from setting that production. But it's possible. We know how to do that. Just a matter of time and staffing. There will be other factors as well.
Okay. Yeah.
I noticed that the L1 level is actually using the QME64 CPU. Is that a limitation imposed by the nesting that you cannot use CPU host as well?
No, not really.
Because it might, feature-wise affect the performance slightly due to some features not being enabled from the
Might be, but it shouldn't be that dramatic, at least.
I mean, I have had situations where using CPU type Nehalem crashes the guest, but using CPU type QME64 or CPU type host does not. So it's possible, but yeah, in terms of performance differences, I haven't seen anything like that happening with.
Yeah, I would use minus CPU widely because it's not what makes a difference, but just to give an example, that this deadline timer is disabled, so it also makes a lot of things less efficient.
I was thinking of, for instance, X280 or something like that.
Yeah,
But not that much. Well, yeah.
Yeah, that will also be.
And the other tests.
yeah. One thing I know about the scalability, so we tested huge, not huge, but like 58 boards running L1 on that kind of SMT. And then L2 focused that L1 VMM it didn't work well. Actually, we failed to install LP. And we reduced the number of ports we are trying to L1 to 4. So obviously we are now some issue with
Some spin lock preemption issues. Yeah, okay.
Nevertheless, we should have bug reports for all of
Yeah,
this.
yeah, but anyway, yeah.
Did you also commit the first level guess, or was it actually on a host that had 64 cores? Okay.
Does anyone use nested virtualization? Oh, good.
Oh, wow. Okay.
At that point, that's about 7 months ago at least, I did detect a problem from that because when I was showing from a functional point of view, the test performance, which the performance seemed okay, but just not really. Yeah. But so I was kind of surprised to learn that this is maybe related to the course research. And also the fact that the disclaimer you have good and that's not exploding.
Yeah.
And as we,
The experiments I did was on the internet work with
the thing is, a few years back, we were pretty much ahead with these features compared to other solutions. And these days, actually, what I receive from some of my customers, for example, the out-of-the-box experience with ESX is quite good these days for nesting. Good with respect to that they actually support it in products. And I'm not sure we are there. So, well, we lost a bit track on this.
Jumping in on that topic, on the next slide, slide 19, you have this overview of what guests were working to
Yeah.
HTTP. And on slide 9, you had mentioned that this is a way also to identify buggy hypervisors. And I wondered, do you have any more insights into why?
No. This is also something which
Good
we
point.
strongly suspect to have a recent regression reason for this. So people were claiming that Xen would work, and I think people tried it recently and it worked. But
Yeah.
something has to be broken here, definitely. So this is also a snapshot, just like this SpecDB benchmark, a snapshot of an unfortunate combination where things went wrong. I don't think it's
Referring to, do you consider these actual lingering bugs in the KVM code, or are you also considering, or do you know of, for instance,
if one line would be broken, I would say it's a hypervisor issue, but that many red bubbles we have here is obviously something, it might be even a single bug which triggers on all these combinations.
The latest we know of is it's probably a regression because of some
We'll
recent
look into
changes.
this also, but what we saw recently, there's a lot of dependencies right now on the level, on the hardware features that are being used by KVM in level 0. So if you're unlucky and you have 2 recent hardware features on your hardware and KVM is trying to use it and stumbles over it while doing nested virtualization, yeah, then something like this could happen. So that's like I did recently with updating my notebook. I ran into some issues with Shadow VMCS. There was a bug lingering there. So if you're unlucky and have a 2 recent hardware underneath and you run into some corner cases, it could happen like this.
So I test regulatory business language, because that's what I had.
Yeah.
And I never used VMware because I never investigated like I actually used it. But usually it's better than that. So SAN works. It has problems with the PC, but it has PC. And I think, I don't remember if it was IOMMU or Virtualization as well. But one of them definitely needs to work. ESX, VMware contributed patches to make it work. So
We don't know. We will follow up on this definitely.
So Mr. Jones was playing with ESX and virtualization and said that's correct. So I also suspect either some setup issue or recent hardware or some recent KVM issue, but that I doubt because I also don't know.
Yeah, ESX, you have to turn off the ESX.
But also they work here, so definitely.
Yeah, well, the ESX problem is setting it up. If we were doing the virtualization, that was different.
And also for ESX, not all cards work, like not all network cards work. So maybe you have the implementation work perfectly, but you sample into some environment.
Just no issue. I run Bandan on KVM, but it's not truly nested virtualization because I run virtualized VMCS within Zen. But I get issue with virtual devices, so I have to use fully this device or something like that to get access from DOM to virtual something.
And thank you again.
Thank you.